So now that we're talking about z being a function of x and y, and we talked about the domain of z, it makes sense for us to now talk about the limit of our function z. I'd like to review single variable calculus and the formal definition of a limit. So you've probably seen the epsilon delta definition. Maybe you didn't understand it, but basically this definition, which is that the limit as x approaches some value a of the function f of x is equal to our limit L if for every epsilon 0 there exists a delta greater than 0, such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So that's just a lot of notation. What does it really mean? Well, let me go down to this first graph, and I'm just going to graph some function f, and I'm going to pick some a value to approach. Basically, this absolute value of x minus a between 0 and delta, that's an interval. It's an interval around our value a, and the absolute value of f of x minus L less than epsilon is also an interval. It's an interval around our limit L. So notice that if I look at this value a, and remember we don't have to reach a, we just have to get arbitrarily close. It's going to correspond to some value, some y value, which we'll call L. Basically, what the definition is saying that for every interval around L, and this interval is going to be some distance epsilon, so this distance here is epsilon and epsilon. So if you take any interval around L, you should find a corresponding, and here's how we find the corresponding, is we take our interval and we map it to our curve and come down. So you should find an interval around A, and notice that on one side of A the distance is smaller, so we typically will choose the smaller distance to be our delta, and then I go out delta. So again, what this says is that if for any interval around L, if you can find a corresponding interval around A, so delta is just that distance from A, so that if you pick any point inside the interval around A, you should get a corresponding y value in the interval around L. So if for every interval around L you can find an interval around A, so that all the points, all the x values around A go to a y value around L, then that's the limit. So it's just talking about getting these intervals, finding these intervals. So if you can find the interval for every epsilon, then that limit exists. So what we're going to do now is we're going to look at some region in the xy plane. And I'll just look at this, some random region. And let's say I have some point, or this is an x and a y value. And let's say that this corresponds to some z value. And in fact, if I take any point in this region, let's say that it just goes to some surface z. Well, does the limit exist as we approach this x, y value? Well, it exists if we can find some interval around this point. The problem is that these are points x and y. So instead of an interval, what I'm going to do is go some delta distance out and find what we call a disk. That disk is described looking at intervals around x and y. So if for every epsilon, and here this is going to correspond to some z value. So if for every epsilon you get an interval around L that corresponds to a disk around your point xy, such that for every point inside the disk you get a corresponding point within that interval around L, then the limit exists. So again, we're looking at intervals. Around our L value. So if you have a single value, L is just a single z value. If you have a single value, you're looking at intervals. But in the case where you have more than one variable, like we have points x and y, then in that case you're looking for a disk around your points x and y. Let's go back to the two-dimensional graph. So remember that the limit exists if all paths lead to the same L value. So that means as I approach A from either the left or the right, both paths coming from left and right should lead to this L value. So I have a problem when I'm looking at multivariable calculus. Okay, so I can come in on some linear paths. Remember, for the limit to exist, every path has to give you the same z value. However, unlike single variable calculus, where I have at most two paths, here I have infinitely many paths. Not only can I approach this point xy horizontally or vertically, I can also come in with a parabolic path. Every single path that I can possibly come up with has to lead to that same L value. I can have a periodic graph, like a sine cosine. So since there's infinitely many paths to approach this point xy, sometimes it's impossible to show if the limit exists. So let's pause for a second, and we'll go ahead and look at the limit of a function of two variables. So let's say that we have some limit L as our points xy approach some point AB. And this is how we have to write it. We have to say that the x and y values approach this point AB because it's an ordered pair of our function. Well, we can replace the xy with some generic p-value point, and it can approach the other p sub 0. That would be our AB. And this is how we can write the limit as well. So that limit does exist if, given any epsilon, you can find a delta, so that your z function minus L is going to be less than epsilon whenever our point xy is, remember this is an absolute value, it's a distance away from my limit point. If this distance is between 0 and delta. So this square root, that's just the distance between any 2 points in the xy plane. So you can replace that absolute value notation with our distance formula for 2 points. So that's a lot of notation. But basically what we're saying is in multivariable calculus, sometimes it can get a little bit tricky to compute our limits. So let's look at some properties that we have with limits, and these are going to be the same properties that we had with single variable calculus. So number 1, if you take the limit of a constant, it's equal to a constant. 2, if you take a limit of a single variable x, it's going to be equal to the a value that x is approaching. The y value doesn't matter here because y value is not in the limit function. But in 3, notice that our function is just y, so in that case it's going to be equal to our b value. So that would be as y approaches b. And then we have limit laws, same as the limit laws from single variable calculus. If you have some function f with a limit L, some function g with a limit m, then if you take the limit of f plus g, you just have to add their limits. If you subtract them, you subtract the limits. If you take a constant multiple times your function, then you could take that constant multiple times the limit. Multiplying 2 functions, multiply their limits. Dividing 2 functions, divide their limit, provided the denominator is not equal to 0. Power function, you can take the limit and raise it to the nth power. And you can do that with not just to the nth power, you could do that for any rational power. Right? The limit is just going to be the limit raised to the mn power. Let's go ahead and evaluate limits. So let's say we want to find the limit as our point xy goes to the point 1, 4. Well, the first thing we always do when we evaluate limits is we plug and chug. So plug and chug just means put in those values. If you get a number back, you're done. Okay? So what I'd like to do is put in 1 for x and 4 for y in this expression to get 2 times 1 squared times 4 squared plus the square root of 1 times 4. So notice this is going to be 2 times 16 plus the square root of 4, which is simply 32 plus 2, or 34. So I put in my xy value 1, 4. I got a number back. 34 is the limit. So this is best case scenario. Plug and chug. Let's try another one. This time our xy is approaching the point 1, 2. So I'm putting in 1 for x and 2 for y. And it looks like I'm going to have 1 minus 2 over 1 plus 4, which will give me a negative 1/5. I put in the value, I got back a number, I'm done. But it may not be. So our region that contains our points x, y, sometimes it'll have a boundary. And if it has a boundary, sometimes the limit will exist on the boundary point, sometimes it won't. So let's look at some vocabulary, and then we'll refer to the diagram here when we talk about this vocabulary. We're going to look at interior and boundary points. So let's say we have this region R, and let's look down at this figure 14.40 down below. Here, this pink region is our region R. It's in two-dimensional space. An interior point P lies entirely within R. So if you look at this point P here, this point P is entirely within the region R, so it's an interior point. What that means is it's possible for us to find a disk where P is the center, and if we pick any point inside this disk, these points will only be points that are interior inside R. So an interior point, you can find a disk around it where all the points in the disk are inside R. However, if we're talking about a boundary point, and here if you look at the point Q, imagine this region R continuing through. So a boundary point Q lies on the edge of our region R. What that means is that every single disk that I can draw around Q, where Q is the center, every disk is going to contain at least one point inside R and at least one point outside of R. And I can make that disk as small as I want. If it's a boundary point, where the point is the center of the disk, I should always be able to find one point in and one point outside of R. Example 2, we have this region. These are all points x and y, so that x squared plus y squared is less than 4. So we want to describe the boundary and interior points of R. Does R contain its boundary points? So first of all, notice that x squared plus y squared less than 4, if I just replace the inequality with an equal sign, I get a circle with a center at the origin 0, 0 and a radius of 2. So that's the boundary. Replace the inequality with an equal sign. So the boundary is a circle with center at the origin 0, 0 and radius 2. So the interior points, since this is strictly a less than 4, the interior points are all points inside the circle. So the interior points, all points in the circle. And here I'm going to restate the equation of this circle. So those are my interior points. Since this is strictly a less than, our region R, it does not contain its boundary points. If it was a less than or equal to 4, then our region R would contain its boundary points. So when we talk about these regions, these are just sets. Now it's important for us to discuss what an open and closed set is. So any region R is open if it consists entirely of interior points. It's closed if it contains all of the boundary points. I'm going to go back to this pink diagram. If I were to draw a solid, let me do it this way, a solid boundary for this region, then our region R would contain all of its boundary points and it would be closed. So let me change that. Let's say that I were to draw this dashed. What that means is that our region R does not contain any of its boundary points. And in this case, R would be open. In example 3, we have this region. Absolute value of x is less than or equal to 2. Absolute value of y is less than or equal to 3. And we want to see if it's an open or closed set. So first of all, I'm going to just do a quick sketch of my xy plane. The absolute value of x being strictly less than or equal to 2. I'll pretend like this is 2 and negative 2. And y less than or equal to 3. Because it says or equal to, it means that this region does contain its boundary points. So it's closed. So here's our region R. And it contains its boundary points and it's closed. Okay. Example 2, is this open? Let's go back to example 2. Notice that it's strictly less than. It does not contain boundary points. So example 2, it's an open set. So the last thing this question asks is to sketch a region that is neither open nor closed. So I'm just going to simply use the region we have before. I'm going to contain the boundary points and not contain the boundary points. So this is an example of a set that is neither open nor closed. And I'm going to just kind of fill that in. So if I were to define this set, it would be all points x and y such that, so notice that it's solid as we go through 2 and negative 2. Such that the absolute value of x is less than or equal to 2. And if we go through our y values, the horizontal, notice that this is dashed, so it doesn't contain boundary points. So the absolute value of y is strictly less than 3. So closed means contains all boundary points. Open contains no boundary points. Neither open nor closed contains some boundary points. This would be a good time to review indeterminate forms of limits. So all of these forms, if you're evaluating a limit and you get any of these indeterminate forms, remember what that means. It indicates that the limit must be evaluated in an alternate way. None of these mean the limit does not exist. None of these mean 0 or 1. It just means you have to evaluate the limit in another way. So with limits, you plug and chug. If that doesn't work, try some algebra. In example 5a, I want to evaluate this limit. When I plug in 0 for x and 0 for y, I get 0 over 0. That's an indeterminate form. That means I should probably try some algebra to simplify this. So the first thing I notice when I look at this limit as xy goes to the point 0, 0, is that it's factorable. This is x plus y times x plus y over x plus y. So you can see you can cancel a factor of x plus y in the numerator and the denominator, so that our limit as xy goes to the point 0, 0 is simply equal to x plus y. And now when I plug in 0 for x and 0 for y, I simply get 0 plus 0, which is equal to 0. If we go back to the original expression, if x and y approach the point 0, 0, the denominator in this expression is undefined. That tells me that this is probably a boundary point. Remember, when we talk about limits, we're just getting really, really close to the value. We don't actually have to reach it. So in this case, it's a boundary point, but it's not contained in the region because it makes our expression undefined. Let's try another one. If I'm going to evaluate the limit as xy approaches the point 0, 2, it's going to be equal to 0, 2, this is 0 over 0. So again, I get an indeterminate form. It does not mean the limit does not exist. It just means I have to do something else. So I'm going to try some algebra. What I notice is that I have a square root in the denominator. So maybe if I conjugate and reevaluate, I'm going to take this limit and I'm going to multiply the numerator and the denominator by the conjugate, so stays the same, the minus turns to a plus. So it stays the same, the square root of x plus y, square root of 2, they stay the same, but the subtraction turns to the addition. Oops, that's going to be a minus. And this will be my plus. The point of doing that is to get rid of the square root in the denominator and then reevaluate. I'm going to leave the numerator unfactored. I'm not going to multiply this out because something nice might happen to where I don't have to multiply all of this out. In the denominator, it turns into x plus y minus 2. That's just one piece. So now I notice this common factor can cancel when I rewrite my limit. And I have to do this. I can't just simply say what the limit is from looking at it right now. I have to rewrite this. Square root of x plus y plus square root of 2. Now when I put in 0 for x and I put in 2 for y, this limit is equal to the square root of 2 plus the square root of 2, which is simply 2 times the square root of 2. And I'm done. So again, the original 0.02, it made my expression undefined because that's a boundary point, but it's not contained in the region. Well, if you approach a value, you plug and chug and you get a number, you're fine. That's the limit. If you get an indeterminate form, you play around, do some algebra, you get a number. When you reevaluate your limit, you're done. That's the limit. That's the value that your function's approaching. So what if algebra doesn't work? Typically, what we do with single variable calculus is we break up our limit and we come in from the left and the right, because those are the only two possible paths. And if coming in from the left and coming in from the right, you get the same value, that's the limit. If you get different values, the limit does not exist. Again, the problem happens in multivariable calculus. Problem happens with infinitely many paths that lead to the same point. It's impossible to check every single path. Remember, for the limit to exist, every path has to lead to the same z value. So since it's impossible to check every path, then the next thing we should try to do is try to show that the limit does not exist. So if a limit does not exist, then all you have to do is have your function approach two different values. That's all you have to do. Find two paths where the limit is different. If you can do that, then you've just shown that the limit does not exist. And you don't have to go through checking every single path, which is impossible. So let's look at example 6. We want to evaluate this limit. Well, the first thing I want to do is plug and chug. I'm going to put in 0 for x, 0 for y, and I can clearly see that this is going to give me an indeterminate form. It's going to give me 0 over 0. Indeterminate. Let's try some algebra. When I look at this, I don't see any algebra that's going to help me. So now, since I can't see any algebra that's going to help, and it's impossible for me to check every possible path that approaches the point 0, 0, what I'm going to do is I'm just going to create different paths and see if I can show that the limit does not exist. I'm not going to graph this function. What I want to do is just look at the point 0, 0. That's the point we're approaching. Well, one thing I can do is I can take this point 0, 0 and I can approach it with a horizontal path. I can also approach this point with a vertical path. So right now I'm looking at this region where I'm approaching my x and y values in the x and the y plane, and I'm approaching 0, 0. So if I want to approach using a horizontal path, then that would be where y is 0. So I'm going to let y equal 0. So if y is equal to 0, I'm going to rewrite this limit. And now I no longer need the ordered pair x and y because I'm setting y equal to 0. So really I'm just looking at x approaching the x value of 0. In my expression, if y is equal to 0, it becomes 0 over 2x squared. So that's simply the limit as x goes to 0 of 0. And the limit of a constant is the constant. So I came in and I approached the point 0, 0 on this horizontal path. Now I need to find another path, and hopefully the limits will be different. So this time I'm going to look at this vertical path. That vertical path happens when x is equal to 0. So now I'm going to let x equal 0. And I'm going to reevaluate our limit. Since x is 0, I only need to look at the y value approaching 0. This is 0 over negative y squared, which is simply the limit as y goes to 0 of 0. That's equal to 0. Okay, so I found two paths that approach the point 0, 0. Unfortunately, they both have the same limit. This does not prove that the limit is 0. It just shows that I found two paths that approach 0. So I'm going to try another path. What if I look at this path here, this diagonal path? That happens when y and x are the same. So I'm going to let y equal x, right? Because this is that diagonal line, y equal to x. So here's a third path. All right. In my limit, what I'm going to do is I'm going to replace my x value with y to get the limit. As y goes to 0, because I'm going to replace the x value with y, of y squared over 2y squared minus y squared. And this would just be the limit as y goes to 0 of y squared over y squared. That's just 1. So the limit of the constant 1 is equal to 1. And I'm done. Notice that I came from two different paths and I got two different z values. So since 0 is not equal to 1, at this point I could say that the limit does not exist. So I found two paths that had a different limit. Well, this doesn't seem like a very efficient way because you're basically just trying a bunch of different paths. And what if all linear paths lead to 0? What if that did happen? Well, then I would have to find different paths. Maybe the sine function. It passes through 0, 0. Or a parabola passing through the point 0, 0. So here's an alternate method. Well, what I'm going to do is I'm just going to let y equal to any line passing through the origin. Go back to this graph. So y equal to mx. That is every single line passing through our origin. If I just adjust my slope m, that gives me a different line, but they all pass through the point 0, 0, and that's what my function is supposed to be approaching. So I'm going to let y equal to mx. In my limit, I'm going to replace the y with mx. So now my expression only has x's. This becomes mx squared over 2x squared minus m squared x squared. So all I did was replace the y value with mx. Let me simplify this. This becomes the limit as x goes to 0 of m, because all the x squareds will cancel, over 2 minus m squared. Notice that I'm looking at x going to 0. There's no x in that expression. We treat it as if it were a constant. The limit of a constant is simply the constant. So what this is telling me is that all I have to do is adjust my slope, my m values, to find different L values. For example, if I let m be equal to 0 in this expression, I get 0 over 2, which is 0. So that means the limit, if m is equal to 0, L is equal to 0. And then I'll just put in another m value. I'll try 1. If m is equal to 1, then this limit is 1 over 1, which is 1, and I'm done. The limit does not exist because I got two different values. So the reason why I chose y is equal to mx is because if we go back to our expression, I notice that if I replace the y value with mx, I get an x squared in the top. And the y squared in the denominator will also be an x squared. So I notice that all my x's turn into x squared and I don't have any y's, which means my y's are gone, but then my x's are also gone. So the goal here is to find some generic path, and in this case I simply used a generic linear path, so that in the end all you have to do is put in different m values and you can stop and say the limit does not exist once you find two different m values that give you two different limit values. So that's what we have at this next bullet. Sometimes linear paths don't work, and we need another method. So we want to choose a path that will eliminate x and y, leaving an expression with only your m value. Example 7, if I evaluate this limit, I get 0 over 0. Oops. So I know it's an indeterminate form. When I look at it, I don't see any algebra that's going to help me. What I do notice is that I have an x to the fourth and x to the fourth, but the y is squared. So if I simply square that and replace the y with an x, I'll get another x to the fourth. So a linear path is not going to work. What I'm going to do is I'm going to let y equal mx squared. So this is simply a family of parabolas where the vertex is the origin. And as we change our m values, that's a sad one, all we're doing is changing the width of our parabola. And if m is negative, then we'll have parabolas that open downward as well. The point is all of these parabolas are going to pass through the point 0, 0. So I've got an infinite number of paths that are going through the point 0, 0 that we're supposed to be approaching. I also note that when I reevaluate this limit and replace my y value with mx squared, that means I only have x's left. I have 2x squared in the numerator, x to the fourth, plus m squared, x to the fourth. If I were to evaluate this limit right now, I still get 0 over 0. I still get the indeterminate form. So if I simply divide top and bottom by x to the fourth, I end up with 2 over 1 plus m squared. And if I take that limit as x goes to 0, it's simply 2 over 1 plus m squared. So let me try some different paths. If m is equal to 0, that means I'm approaching the value of 2. If m is equal to 1, that means I'm approaching the value of 1 and I can stop. I got 2 different limit values. Since 2 does not equal to 1, my limit does not exist. So to recap, when you're evaluating limits in multivariable calculus, the first thing you do is plug and chug. If you don't get a number and instead you get an indeterminate form, try some algebra. If that doesn't work, the limit probably does not exist. So instead, try to find 2 different paths that give you different limits. What goes hand in hand with this idea of limits is the idea of continuity. And it's going to be the same definition that you had in single variable calculus. When we talk about a function being continuous at a point, some point a, b, well, 1, it has to be defined. There cannot be a hole at that point a, b. The limit has to exist. And the third criteria is that the limit has to equal the value of the function. So if all 3 things are true, then our function will be continuous at a point. So some common functions that, and we can use this when we talk about continuity, that are continuous would be polynomials, and this is on their domains: rational functions, log functions, trig functions, exponential functions. Remember, if you have a continuous function or more than one continuous function and you add continuous functions, you get a continuous function. Subtract continuous functions, functions continuous. Multiply, divide. If the functions are continuous and you compose them, they're still going to be continuous. In example A, we're going to determine where this function is continuous. Well, I see that I'm going to have an issue at the point 0, 0, because this is a piecewise function and it breaks off into 2 different functions at the point 0, 0. So where is this continuous? Well, I have to discuss this whole function. I can't simply say, oh, well, just at 0, 0, it's not continuous. That's not true. So first of all, let's look at what happens if our point is equal to 0, 0. So if we're looking at points equal to 0, 0, then that means we're looking at z equal to 0. Well, z equal to 0 is a constant function. And in fact, it's a polynomial. It's a constant polynomial. Polynomials are continuous for all values. So z equal to 0 is a polynomial, so it's continuous. For all points x, y in R2. So it's continuous everywhere. So notice that if our point is not equal to 0, 0, then we're looking at z equal to 4xy squared, over x squared plus y to the 4th. This is a rational function. And rational functions are continuous on their domain. And I'm going to use CONT period for continuous because I'm getting lazy. Okay. So what I'm doing with all of this is I'm checking all the pieces because we're supposed to discuss where it is continuous. So what is its domain? Well, the domain is all points x and y, so that the numerator is not equal to 0. This is the domain. As long as the denominator is not equal to 0, then we're good. However, when you look at that, and I probably shouldn't have written this as equal to 0 because these are points x and y, so it should be not equal to the point 0, 0. But we're fine because in our definition, we're assuming that the point's not equal to 0, 0. So it's continuous on those two separate pieces. What happens at the point 0, 0? So at 0, 0 is where this function may not be continuous. So since I'm discussing continuity at a single point, I'm going to check all the criteria. Is it defined? What is f of 0, 0 equal to? It's equal to 0. It's defined. Does the limit exist? I don't know. The limit as xy goes to the point 0, 0 is indeterminate. So I can try algebra. I can see algebra is not going to work. And the next thing I want to do is see if I can get rid of something. Let's see. If x is a y squared, my numerator becomes y to the 4th. In the denominator, I'll have y to the 4th plus y to the 4th. So all my y's will be to the 4th power. I'm going to let x equal my squared. So this limit will be as y goes to 0 because I got rid of the x by having it equal to my squared. Numerator becomes 4my to the 4th. Okay, and then the denominator becomes m squared y to the 4th plus y to the 4th. So that's going to be equal to the limit as y goes to 0 of 4m over m squared plus 1. And that limit would just be 4m over m squared plus 1. If m is equal to 0, and I always start at 0 because they're easy, then the limit is going to be equal to 0. If m is equal to 1, my limit is going to be equal to 2. So I found two paths, gave me different limit values. The limit does not exist. So that second criteria, limit exist, it does not. Well, what does all of this mean? It means that f is not continuous at the point 0, 0. But we were supposed to discuss where the function is continuous. So we've determined that the function is not continuous at the point 0, 0. But in our previous discussion, when z is equal to 0 or z is equal to 4x y squared over x squared plus y to the 4th, those two pieces are continuous. So what we can conclude is that f is continuous for all points that are not equal to 0, 0. So for all points x, y not equal to 0, 0. In single variable calculus, we talked about continuity of a composition of functions. And we have it for our multivariable calculus as well. So if we compose two functions, g and f, then if it's continuous at both of those pieces, that's basically what it's saying, then when you compose them, it's going to be continuous. Example 9, we're supposed to determine where the function is continuous. So I'm going to decompose it. I'm going to look at the argument here, the 2x squared plus 3y squared. I'm going to look at that as being my u. So this is a composition of two functions, this u and that means that my z, I'm going to call that the natural log of u. So I have a composition of function. I'm calling z the outside piece, the natural log piece. I'm calling u the inside piece, the argument on the natural log. Well, if we look at u is a polynomial. So u is a polynomial. It's going to be continuous for all points x and y. Okay. But z is the natural log function. So z is continuous for the argument strictly greater than 0. So logs are only defined when their arguments are positive. They cannot be 0 or negative. So what that tells me by this theorem is that my function is going to be continuous. That is a terrible O. It's going to be continuous where the argument 2x squared plus 3y squared is strictly greater than 0. So that's my u. Now notice that with this inequality, since I'm squaring my x and squaring my y's and I'm adding these together, they can never be negative. And the only way I'm going to get 0 is if both x and y are 0. So I can conclude that f is continuous for all points x and y that are not equal to the point 0, 0. So we talked about single variable functions. Now we're talking about functions of two variables. So z is our function, x and y are our variables. But it's possible mathematically to look at functions of three variables and even more. So if we're talking about functions of three variables, same rules and the same properties. I'm not going to draw a picture because I don't know how to draw a picture once I start getting into fourth dimensional space. But I can still evaluate the limit. Notice that we have this ordered triplet, x, y, z, and in this case it's approaching the point 0, 0, 0. So the first thing I'm going to do is just put in 0 for x, y, and z. And unfortunately I get 0 over 0, which is indeterminate. I can't see anything algebraically that I can do, so what I'm going to do is see if I can find two different paths. it's a little bit trickier. It's a little bit harder to find some generic equation that has an m in it, because our goal is to get rid of two variables and have one left over. So instead, I'm just going to look at what happens when, say, x is 0 and y is 0. I'm just going to plug in, and that's because my x value is approaching 0 and my y value is approaching 0. So why don't I just plug in 0 for x and 0 for y? Then my limit is just a z value, and it's approaching 0. I'm going to have negative z squared over positive z squared. If I were to evaluate the limit right now, I would get the indeterminate form, 0 over 0. So I'm going to algebraically simplify this to get the limit as z goes to 0 of negative 1. Now when I evaluate the limit of this constant, I get negative 1. So setting x is equal to 0 and y is equal to 0, I'm just looking at that single path along the z. Let me find another path. Let's do x0, z0. Our limit now just has y. And it's going to be 0 over negative y squared, which is equal to the limit as y goes to 0 of 0. And the limit of a constant is that constant. So notice that I got two different limits. The limit does not exist. So we can still do all the properties we did with our previous, even though I don't even know how to visualize this function xy plus yz minus z squared over 2x squared minus y squared plus z squared, since it's fourth dimensional space. But I can do the math there. So that's it for this section.